Okay, so let's have a look at the 2020 Higher Level Leaving Cert Maths Paper 1, question 7. So in part A here we have a number of the form 1 plus 2 plus 3 plus all the way up to n is sometimes called a triangular number because it can be represented as an equilateral triangle. The diagram below shows the first three terms in the sequence of triangular numbers. So we have to complete this table here listing the next 5 triangular numbers. So let's have a look at that. Now we can see here we got 1, we got 3, we got 6. If we were to continue that on, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I can put 10 in here. And let's see, let's go again. 11, 12, 13, 14, 15. So now I'm up to 15 here. Let's try again. 16, 17, 18, 19, 20, 21. This is 21. Do another one. 22, 23, 24, 25, 26, 27, 28. So now we have 28 here. And the last one is 36. I'm just running out of room here, so it's 36. So our answers are 10, 15, 21, 28 and 36. Okay, so the second question then is this one here. It just says the nth triangular number can be found directly using the formula Tn is equal to n times n plus 1 over 2. And we're asked then, is 1275 a triangular number? Give a reason for your answer. Well, let's just say 1275 is equal to n times n plus 1 divided by 2. Now, if 1275 is a triangular number, n then should turn out to be a natural number, a whole number, natural number. So let's do that. First thing I'm going to do is just multiply across by 2. So if I do that, I get 2550 is equal to n squared plus n. Just multiplied out the brackets, and that'll give us n squared plus n minus 2550. Now I can solve that. I can say 0 is equal to, just factorize it first, and I'll get n minus 50 and n plus 51. That'll give me n is equal to 50 or minus 51. Now we can ignore the minus 51. N couldn't possibly be a negative number, has to be a positive number, so n is equal to 50. So as n is a natural number, so it's equal to 50, 1275 must be a triangular number. Must be a triangular number because n is a whole number, a whole positive number. And that's it for part 2. So let's have a look at part B, 1. The n plus 1th triangular number can be written as Tn plus 1 is equal to Tn plus n plus 1. So any number can be written as the previous term plus n plus 1. Now where n is a natural number, write the expression n times n plus 1 over 2 plus n plus 1 as a single fraction in its simplest form. So let's do that then. So we have n times n plus 1 over 2 plus n plus 1. And that's over 1 if you like. So just work over this way. Our common factor here is 2. Our lowest common multiple here is 2. And on the top then we've got n times n plus 1. Plus is here, and then we got to double the 1 here on the bottom, so we got to double the top as well, 2 times n plus 1. Now if we just come over here then we end up with n squared plus n plus 2n plus 2 all over 2, and that'll give us n squared plus 3n plus 2 over 2. Or we can factorize the top and just say n times n, 2 times 1, 2 times 1, and it's going to be plus plus, and that's over 2. So that's it really. We've added those two fractions, and that's it. Okay, so part 2 then, we've got to Prove that the sum of any two consecutive triangular numbers, will always be a square number, i.e. a number of the form k squared where k is an element of n. Okay, so prove that the sum of any two consecutive triangular numbers. Now if we look back up here, we can see that the n plus 1th triangular number can be written as Tn plus n plus 1. This is Tn, and this is n plus 1. We've added them and we've gotten this here, or we've got this here. So we can use that in this question. So what I'm going to do then is just take my Tn, which we know is n times n plus 1 over 2. I'm going to add the next term, which is, well, it's really, I'm going to use the n squared plus 3n plus 2 over 2. So I'm using this version here. I'm just going to add those two. We have to add the Tn, or the nth term, and the n plus 1th term. That's what we're doing. So let's do that and see what we end up with. We should end up with a square number anyway. So let's add these two. We end up with, I'm going to just multiply out this bracket here, so it's n squared plus n squared plus 3n plus 2. And if I do that, I'll get 2n squared plus 4n plus 2 all over 2, and I can see that I can divide the 2 into the 3 terms on the top. So I'll just move it over here a little bit, and what we end up with here is 2 into 2n squared is just going to be n squared. 2 into 4n is going to be 2n, and 2 into 2 is 1. And that's not over 2, that's what we get. All I've done is divided the 2 into each of these 3 terms. So this here you can see is just, if we factorize it, it's just going to become n times n, 1 times 1 plus plus, so that's just going to be n plus 1 squared. Now we know that n is a natural number, and n plus 1 therefore is going to be a natural number. So it's going to be our k squared here. So n plus 1 is our k, and we're squaring it. So in other words, when we add two consecutive triangular numbers, the result will always be a square number, n plus 1 squared. Okay, so let's have a look at the next one then. Two consecutive triangular numbers add up to 1, 2, 5, 4, 4. And remember, this here is what we get when we add up two consecutive triangular numbers. So, in other words, n plus 1 squared should give us 1, 2, 5, 4, 4. Find the smaller of these two numbers. Well, the first thing we've got to do is find what n is, so let's do that. Okay, so the first thing I'm going to do here is just square root both sides. So I've got n plus 1 is going to be equal to plus or minus the square root of 1, 2, 5, 4, 4. So that will give me n plus 1 is going to be equal to plus or minus 1, 1, 2. So that just means then that n is going to be equal to, well, if we take plus 1, 1, 2 is going to be, and subtract the 1 on the left hand side, that'll give us 1, 1, 1. Or if we take the minus 1, 1, 2 and subtract 1, we get minus 1, 1, 3. Now again, we can't take the negative number. N can't be negative, must be positive, so this is the one we're going to take here. Okay, so if n is equal to 1, 1, 1, I should say, what is our triangular number going to be? Well, remember, T111, term number 111, is going to be 111 times 111 plus 1 over 2. In other words, n times n plus 1 over 2. That's the very first formula we were given in this question. So if you work that out, you'll get 6216. 6216. Now, two consecutive triangular numbers add up to give us this number here. So find the smaller of these numbers. So is it this one and the next one? Well, let's check it out. The next one would be T112. If we were to put that into our formula, we would get 112 plus 1 all over 2. And if you do that, you get 6, 6, 3, 2, 8. So these are both triangular numbers because we put them into our original formula. Now they're two consecutive triangular numbers, so if we add them then, 6216 plus 6328, we'll get 8 and 6, 14, 4, okay, 1, 3, and 1 is 4. That'll give us 4 here, 3 and 2, 5, and then 6 and 6, 12. So we do get the number that we were given in the question. So that's perfect. So these are two consecutive triangular numbers. So the question is find the smaller of these two numbers. So the answer then, just do that in right here. So the answer here is going to be 6216, the smaller of the two numbers. Okay, so that's that one. Now the next one, part C. Some numbers are both triangular and square, for example 36. Leonard Euler in 1778 discovered the following formula for these numbers. So nk is the kth number that is both triangular and square. Use Euler's formula to find n3, the third number that is both triangular and square. So all we've got to do is put 3 into this formula. Fairly straightforward question. So n3 is equal to 3 plus 2 root 2 to the power of 3 minus 2 root 2 to the power of 3 all over 4 root 2, and we've got to square that. So look, if you do that on your calculators, that's just calculator work, you get 1225. So that's our answer. That's the third number that is both square and triangular. Okay, so that's it. Let's have a look at part D then. This is a proof by induction. So we have to prove by induction that for all n is an element of n, the sum of the first n square numbers can be found using this formula here. 1 squared plus 2 squared plus 3 squared up to n squared is equal to n times n plus 1 times 2n plus 1 over 6. Now, let's just run through this proof by induction. So what we want to prove is that 1 squared plus 2 squared plus all the way up to n squared is equal to n times n plus 1 times 2n plus 1 all over 6. So we're going to do this in 4 steps. So let's do our first step, and that's just going to be to show that we want to show that the proposition is true for n is equal to 1, or n is equal to 1. So all we got to do is do the left hand side and the right hand side and see are they the same. So the left hand side here is, well, that's just going to be 1 squared, which is equal to 1. The right hand side here, just got to put 1 into the formula, so it's going to be 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. And if we were to do that, we will get 1 and 1 is 2, 2 plus 1, 3, 2, 3, 6. Well, yeah, we'll just get 6 over 6, which is also equal to 1. So, therefore, the left-hand side is equal to the right-hand side. So, P1, the proposition is true for n is equal to 1. P1 is true. Okay, so now we're going to do step 2, and this is just making an assumption here. I'll run through that now. So what we're going to do is assume the proposition is true for n is equal to k. So I'm going to assume that the proposition is true for n is equal to k. So in other words, 1 squared plus 2 squared plus all the way up to k squared is equal to, so it's equal to k times k plus 1 times 2k plus 1 all over 6. So in other words, all we've done is just taken the n here and just replace it with k. That's what we're assuming to be true. Okay, so that's step 2. Now step 3 then is the proof then. We've got to prove. So what we've got to prove then we've got to prove that p k plus 1 is prove that pk plus 1 is true. In other words, the proposition is true for n is equal to k plus 1, given that it is true for n is equal to k. So we're assuming that it's true for n is equal to k up here, and what we're going to do is prove that if it is true for n is equal to k, then it will be true for n is equal to k plus 1. So what we got to prove here then is that 1 squared plus 2 squared plus all the way up to k squared plus k plus 1 squared is going to be equal to, now instead of the k's we put in k plus 1, so it's going to be k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1 all over 6. This is the right hand side here. So let's just simplify that. We have k plus 1 anyway. K plus 1 is k plus 2. 2k plus 1 plus 2 plus 1 is 2k plus 3. And that's all over 6. So that's what we've got to prove. Let's just move that up a little bit. So what I'm going to do is I'm going to take the left hand side here and I'm going to make it look like the right hand side eventually, hopefully. And if you look at the left hand side here, you've got this part here which is just our assumption. That's all of this here. It's all of this here, if you like. I'm going to replace this bit here with this bit here. So let's do that. So we have k times k plus 1 times 2k plus 1. That's over 6. So that's this bit here, or this bit here if you like. And I'm going to add this bit here now. So it's k plus 1 squared. So that's what we're going to work on, and we're going to make it look like this eventually. We're going to manipulate it until it looks like that, hopefully. So let's do that. Now, if we look at the left-hand side then, what we can do is just add these two fractions. So if we add these two fractions, we get a 6 here. This will give us k times k plus 1 times 2k plus 1 plus, now this is a 1 down here, so we've got to multiply it by 6, so we've got to multiply the top by 6. That's k plus 1 squared. Now if we do that, we get, well actually what I'm going to do now is just factorize out this k plus 1. Remember, I've got to end up with a k plus 1 at some stage, multiplied by two other brackets. So I see I've got a k plus 1 here, and I've got two k plus 1s there actually multiplied, so I can factorize out those k plus 1s. So let's do that. So I've got a k plus 1, which I'm factorizing out, and that'll leave me with k times 2k plus 1 here, and then I'm going to add 6 times k plus 1 here, and then that will divide by 6. Let's see, I'm kind of running out of room here, so I'm going to start working over here now. So let's see what this will simplify to. Hopefully it will simplify to this here. Now we have our k plus 1. We have our over 6, if you like. We have our 6 down here. What about the rest of it? The rest of it I've got to make look like this bit here. So let's multiply it out and see what happens. We have a 2k squared plus k plus 6k plus 6. Okay, now let me just move this over. And I'm going to start working up here now. Let's see, what am I going to do now? I'm going to simplify this and factorize it. So we have k plus 1 times 2k squared plus 7k plus 6, and that's all over 6, and that's going to be equal to finally k plus 1. I can factorize this here. We have 2k, we have k. 6 is 6 times 1, which is not going to work, or it's 2 times 3. I'm going to put 2 there, 3 there, so that'll give me 4 and 3, 7, so that will work. And that is what we want to end up with. And you can see we did get this here. If I just move it over a little bit, you'll see we did get the same thing. We have our k plus 1, we have our k plus 2, we have our 2k plus 3 here, and we have our 6 on the bottom. Okay, so just to finish this off then, so we would say, you know, so this is equal to the right hand side. Now, step 4 then is just the conclusion, if you like. So let's write all that out. So we can say that the proposition for 1 is, well, we'll just say is true. And then we can say if pk is true, then we can now say pk plus 1 is true. We've just proved that here. So if pk is true, then pk plus 1 is true. So therefore, by induction, Pn is true for all n is an element of n. In other words, 1 squared plus 2 squared plus all the way up to n squared is going to be equal to n times n plus 1 times 2n plus 1 all over 6. Okay, so that's it for this video.